and where we're at. All right, so we've got, just to kind of keep track of what we've had so far, we've got magnetic force related to charge, the velocity, sine, and then of course we have the sine of the angle. And so FB max is going to be QVB. And then if I'm doing it, this is for a point charge, and if I'm doing it for wire, we can show that FB is equal to BIL sine of the angle, or the max is going to be BIL. And in order to do that sliding one here, we had to set our electric field force to our magnetic field force. We had to set them equal, and that was QE, and this was QVB. Q's canceled, and we get E is related to B. But the really cool part is that this velocity is related back to our magnetic field. So we get that part. Okay. We get that piece. We also get, we talked about the cyclotron radius. So this is the velocity. And then the cyclotron radius we actually showed was MVQB. And these two together will give us our mass spectrometer. And I've actually got a problem for that. And we'll kind of get to that. So this gives us our mass spectrometer information. So the key here is this is really where we start to see that the magnetic field and the electric field are definitely related. And when we ultimately get to electromagnetic waves, which I'm guessing will probably be around next Friday-ish by the time I get through stuff, that we're going to see that piece there. But in order to do that, we got to get through electric motors and generators, and we got to get through a few other things, step-down transformers, and a variety of other stuff. So let's take a wire loop, except we're going to be really deliberate about our loop here. And we're going to have a uniform magnetic field. This side is B, and that side is A, in terms of the sides. Now I'm going to look at it side on, okay? So this side, if I look at this, this is going to be A over 2. I still have my magnetic field, okay? I have my magnetic field. And I'll end up with a force here, and I'll end up with a force there, right? Because we've seen that I get a force. So we're actually going to get kind of a rotation about that axis there. And if I look at the magnitudes of the forces, because the current throughout the whole thing is going to be the same, the magnitude of the force is going to be B I, the length of the side, which in this case happens to be little b. So our forces are going to come in. By the way, this is going to be a couple. Remember when we talked about couples way back when, looking at why an X crossbar tire iron was better or worse, depending on your point of view, versus our regular angle iron tire iron. So if we go back and look at torque, torque is R cross F, right? So we get our torque as R cross F. But if we're looking at the magnitude of the torque, that's going to be FR, which now is going to be FA over 2. But because this is a couple, I can sum them up. And I'm going to have 2 of them. So the total torque is going to be F times A, because I get 2 of these. And I can add them together. All right? I can add them together. So if I put in my force, which is B, I, the length, A, and I have two of them because I have two forces that are additive, I end up with this, but B times A is the area of my loop. That's why we're judicious about picking out our loop at this point. So the torque that we're going to get for turning this loop is BIA, that's the maximum, and I'll have the sine of the angle as I rotate through that I end up with, and I have two of those. All right, now this is for a single loop. Now if I add multiple loops, guess what? It comes up with multiple turns, so now I get to capital N, B, current, A, sine of the angle. And this torque is really what's going to give you your simple motor. All right? That's really what's going to give you your simple motor. Now, we are going to see two different ends. We're going to see this end, which is the number of loops, or we'll see it as the number of turns. And there's this n, this is a little n, and that little n is the number of turns per unit length. So when you did your thing through the slinky, you did with the little n, but I can also have this big N. And it just is a matter of what device I'm using, which way I want to work with it. I want to work with it there. So let's do a quick problem. We're going to calculate the torque on a loop. So we want to calculate the torque on a loop of current, where the current through there is going to be 2 amps. The radius is going to be 1 meter. And the magnetic field that we're going to set up is 0.5 Tesla. I have to calculate area, which is pi r squared. So that's going to be pi 1 meter squared, which is just going to be pi. And we can calculate, if we look at this torque, okay, I can rearrange this, and I can take out the I and the A and the N, and I can define what we call a magnetic moment. And the magnetic moment is IAN, and it's just going to simplify my life a little bit. How many turns do I have? What's the current in the wire, and what's the area? It makes it a little bit easier to work with. So if I do that, this becomes 2 mu B, whatever my magnetic field is, sine of my angle. So I can do that. So if I put that in, I can calculate my magnetic moment, which is going to be my current, which is 2 amps times 1. And right now I have the number of turns, which is 1, so this ends up being 2. This ends up being 2. That's area, sorry. It's 2 pi, number of turns. And that gives me 2 pi n, which is my magnetic moment. And if I calculate the torque, it becomes 2 of those. Because I've got, torque is 2 mu B sine the angle. Now I put my 0.5 Tesla in there, sine of the angle. And our n right now for one loop, I'm going to get 2 pi sine of the angle. And maximum would be 2 pi. And if I have more coils, we get there. Somewhere along the way, we've also defined that B for a solenoid is our permittivity of space, Ni, and that, if I'm looking at my solenoid, is the uniform magnetic field throughout the center. Which, hopefully, everybody in the lab got a nice straight line for the material. And depending on what I've got, I should be able to calculate mu. Be able to get it, provided I've zeroed everything out correctly.
How did you get the 2 pi sine theta? Did you just plug in 1 for the number of terms?
Yeah, plugged in 1 for the number of terms.
Okay.
That's for a single loop. Multiple loops, I have to multiply by. All right, so let's go take a step back a little bit. And we're going to look at getting some equations. So I'm going to flip over here and we're going to talk about some equations first. Way back when, we showed that my electric potential or my EMF, if I went through a closed loop, was E dot product DL. Okay, way back when, it's been a while, got to shake off the cobwebs, but we showed that. We also talked about Gauss's law for electricity, and we said if I went over a closed loop for my electric field, according to the area, that was going to equal whatever the charge inside was divided by the permittivity of free space. And this was Gauss's law. And this is for electric fields. Okay. Well, we've also seen that Gauss's law for magnetism, if I do this, I'm going to end up with this lovely, nice and parallel. And this is also a Gauss's law. So we've got that part. And what we've been seeing from Faraday's experiments and doing a variety of things is that we've seen that a changing current produces a magnetic field, and the changing magnetic field produces a current. And so we can look at our magnetic flux from this right here in Gauss's law, that if I'm at perpendicular, that's going to be my max, or if I'm in a general case, it's going to look like that. Now we can also show that we get an EMF that's proportional to my change in my flux. And if I'm writing it for you guys, I'm going to write it this way. Okay. That my change in flux comes from, and I'm going to get that voltage, and we saw that lovely voltage. And we've seen the experiments, because I've actually put it out there. If I have one loop, it's going to do one thing. If I have multiple loops, this goes up by the number of multiple loops. Well, here comes the weirdness. And this is where we start looking at weirdness. Lenz's law, if I did a Lenz's law tube experiment, I have a tube. And if I drop a marble down the tube, just a good old marble, the marble is just going to fall straight through the tube, and it's going to get down there, and we know that the 1/2 mv squared is going to equal mgh, and the velocity ends up being the square root of 2gh. Just wherever I drop it, it's going to fall down, And we've done that enough times that we know exactly how far it goes. All right, so if I drop a marble down a tube, nothing really happens. Now if I take this tube, and this tube happens to be a conducting material, we're going to take a magnet and we're going to drop it down the tube. So let's think of what's happening with our magnet when we drop it down the tube. So my magnet has my magnetic field, and I have a tube, and as my change in magnetic field happens, I get a current in my wire. When I get a current in my wire, I get an opposite magnetic field, and it puts the brakes on this little magnet. Now in the Lenz's law tube, what happens is there's a force due to gravity versus the force due to the magnetic field that I'm getting. Those are counterbalanced, and I ultimately will have the magnet fall out the bottom. But it's going to take a heck of a lot longer because I get a current, the current generates a magnetic field, it works against the magnet, and it causes the magnet not to fall as fast. And we end up with it. So we get this weird observation, and it's Lenz's law. And it says that the current caused by the induced EMF travels in a direction that creates a magnetic field with the flux opposing the change in the original flux. So we're going to create a magnetic field that opposes the change in the original flux, which means I'm going to put a negative sign right there. I'm going to put a negative sign. And this is defined as Faraday's law. Yeah, there it is. Creates it travels in a direction that creates a magnetic field with the flux opposing the change in the original flux. So we end up with Faraday's law that looks something like this. And what you're going to find is we're going to see Faraday's law written a number of different ways. Okay? We're going to see Faraday's law written a number of different ways, but this is where we start. This is where we start the process. You can also say Lenz's law a little differently, and it's going to make it this way. It makes it make a little bit more sense. It says that the induced current in a loop is in the direction that creates a magnetic field that opposes the change in the magnetic flux. Through the area enclosed by the loop. So that's another way to say it. So basically what's happening is that my changing magnetic field creates a current. The current changes or creates a changing magnetic field, or current creates a magnetic field which is going to oppose the one that I'm coming in there. So we get a negative sign. We get a negative sign. And it's really, really cool. All right. So I'm going to go ahead and skip, like I said, I'm going to skip around a little bit, but then we're going to come back and look at a couple problems. So if I do this, so I'm going to start out with my induced magnetic field with respect to time. We can call this self-inductance. Right? We can call this self-inductance. This negative sign also can create something that we call a back EMF, because it's reversing. So we get something that we call a back EMF. Now, we can re-look at and re-change this so that we have this equivalent to a change in current with respect to time. Or I can do this as dI with respect to time. And we know that these things are proportional, so I'm going to define something called L. And L is going to be dependent upon how many turns I put in there, what material I'm using. It's the thing, and it's just defined as the inductance of the device, or we can say this is the resistance to the change in current. So we can get that as the resistance to the change in current. This L is measured in henries. And it's equal to 1 volt second divided by amps. So if we go back and we look at our solenoid, I've got N is equal to my change in flux, because remember my negative's hanging out there. And this at maximum is going to be the total flux over a given time. And that ends up being current, if I do this right. And for solenoids, if I look at this, I'm going to get L is going to be mu 0, the number of turns per unit length times the length squared, divided by L, and that's times area, which can be simplified with mu, the number of turns, squared, L times area. Or, if I have L times area, that can be volume. And this is for solenoids. go back and let's look at a circuit for a second. So if I have a switch and I have a battery and I have a resistor in here and I have a capacitor in here, when I close the switch, this starts filling with charge, right? We saw that with a capacitor. And we actually saw that if I'm filling it, it's going to raise up till ultimately I get to a Q max. And it's going to have the behavior that looks like this. 1 minus E minus T over RC. And that's for charging a resistor in a circuit. Now what's going to happen now is instead of a capacitor, I'm going to put an inductor in here. And I have my battery. And I have my switch. When I throw the switch here, remember I got E is equal to IR, so I can do the current is equal to E divided by the resistance. But this thing is resisting the current in the system until I get current established. Because this thing wants to resist a changing current. So it's going to resist it. So I'm going to get some function. And it turns out I'm going to get some function that looks an awful lot like what I had for capacitors. Except this time constant is going to be a little different. And that time constant for this system is going to be L over R. The time constant for this one was RC. So we see that these things are doing things to the system in different ways. It's going to take a little while for my capacitor to charge up before I let current through. This is fighting the changing current, so it's going to take a little while before it's going to let the current pass through. So we can get that thing that's there. This also leads us to the energy of these things. So my potential energy associated with this is going to be 1/2 Li squared. And remember, my potential energy associated with my capacitor is 1/2 CV squared. So we will store energy with the magnetic field. We're storing energy in an electric field. So this is storing energy in electric field. This is storing energy in the magnetic field. So let's do a couple problems here. So we want to calculate the induced EMF and current for a 25 turn coil. Now, it's going to have an area, well, it tells us that it's a square coil, and it's going to have 1.8 centimeter sides. And we're given the resistance of the coil being 0.350 ohms. And we're going to change the magnetic field from 0 Tesla to 0.5 Tesla in 0.8 seconds. So So we're gonna have a changing magnetic field. We're given a coil of 25 turns. It has 1.8 centimeter sides, and we have that resistance. So I've got to look at my change in flux with respect to time, which is going to be V times the area over time. My magnetic field is going to go from 0.5 from 0. My area, I'm going to have to convert my 1.018 meters, has to be squared, because I'm going, if that's a square side, it's that times that. That gives me my area divided by 0.8 seconds. And that gives me if I do that, that. And then if I do this, I have to put my N in front. So I've got 25. And this, this ends up being 1.62 times 10 to the minus 4 divided by 0.8. And that gives me, and that has a negative, gives me a negative 5.06 times 10 to the third volts. And if I want the current, that's just my change in potential divided by the resistance, which gives me my negative 5.06 times 10 to the third divided by my 0.350, and that gives me a negative 1.45 times 10, yeah, just a second. And if I have my magnetic field like this, the current is actually going in that direction. Oops, now you can't see that. My magnetic field goes like that. The current actually goes in the clockwise direction as viewed from the top. I've got a wire that looks like this. Did I do this problem for you guys? Current goes in there. We want to calculate the magnetic field where this is a radius R. I'm going to calculate the magnetic field that's at that spot. We can do that the little magnetic field is going to be related to mu divided by 4 pi, whatever the current is, sine of the angle r squared dl. And if I look at this dl and this dl, and then I've got the dl that goes around there, this one, if I'm doing it this way, that says dB is equal to 0 for that one. If I'm doing it this way, dB is equal to 0. So I'm only having to worry about the curve. And that ends up being that if I do this part where I'm dealing with the curve, I'm going to get dl over the radius squared as I'm going from my limits of 0 to pi over 2 r, because I'm going to go from 0 to pi over 2 there. So I'm going to have that limit. So I end up with B is equal to mu I 4 pi squared, the integral from 0 pi r over 2 dl, and that gives me mu I, and it works out to be 8. Pi's cancel, and I get 8r. Just kind of going back and catching a couple of problems that we haven't done. So L, if I'm doing the inductance of a device, we get mu n squared area L. I can also write this in terms of mu n squared L times the area. Because remember, little n is the number of turns per unit length. N is just the number of turns. So you can have either of those expressions. So we want to calculate L for a 300 turn length, or 300 turn solenoid of length 25 centimeters and an area of 4 times 10 to the minus 4 meters squared. So L is going to equal mu n squared LA, because that's what we've been given. So I'm going to get my 4 pi times 10 to the minus 7. I have 300 turns squared. The area is 4 times 10 to the minus 4 meters squared, divided by 0.25 meters. And that's going to give me 1.81 times 10 to the minus 4 henries, or 0.181 millihenries. I think I got time for one more, and it's the mass spectrometer problem. So for my mass spectrometer, we said that V was going to equal E over B, and we said that R was equal to MVQB. And we want to determine the relative abundance of oxygen 16 to oxygen 18. We're given that E is equal to 4 times 10 to the third volt meters, and B is given by 0.08 Tesla. We're told that these are going to be ionized oxygen, so they're going to have a charge of 1 times 10 to the 1.76 minus 619 coulombs. So we're going to need the mass of the oxygen 16, and we're going to need the mass of the oxygen 18. And that's nice, because that's going to be 16 times my proton or my neutron. And that's going to give me 2.66 times 10 to the minus 26 kilograms. This gives me 18 times 1.66 times 10 to the minus 27. Gives me 2.99 times 10 to 26 kilograms. My velocity is easy enough. You just take E divided by B, and that's going to give me 5 times 10 to the 4th volt Tesla meters. My volt is a joule coulomb, and I end up, and a joule is a Newton meters. So I end up with an extra 1/meters, and my Tesla, it works out to be a Coulomb Newton seconds. No, the Tesla meters works out to be that right there, Coulomb Newton seconds, so those cancel, Newtons cancel, and I end up in meters per second. Remember, units get funky. Because 1 Tesla is a Newton second Coulomb meters. So you get weird stuff. I can do my R for 16 and my R for 18. You're just plugging in the values there. Up here, you're just plugging in those values. And R ends up being 0.104 meters. And this R becomes 0.234 meters. And so they'll actually, if I'm looking at my detector, one will hit here and one will hit over there. And I'm going to lose Enid in like a minute. And we will start rotating and start looking at alternating currents and things like that on Friday. So it looks like to get where I need to be, it looks like we're going to have a test probably not next Friday, but a week from that Friday. That would be my gut feel. 2 weeks from this Friday, so it'll be like the 15th.
The last one.
Yeah.
Look at the last one.
And that'll be over magnetism.
Oh, yeah.
And it will be open book, open notes, all that lovely stuff, because with magnetism, it's to do just a one-page cheat sheet, not necessarily easy to do. So it's open notes, open book, open everything, except access to the internet. You can't have access to this.
We're gonna have